Okay, and here we go. This is video 5. We're going to say of 6 unless something crazy happens. So here we go. This is just another problem. So we just saw an example of one problem. Now it's going to be a very similar problem. I encourage you to write these out on paper, and there's plenty more problems I'd like to say. On the PowerPoint slide that's on, I'm not doing them all in class here. There's plenty more examples actually on the website. So in this lecture that's on Blackboard right now, in the PowerPoint folder. So, but notice this one, assume a method of counting cards. So we, rounders, counting cards, going to Vegas. It's kind of a cool idea, and you can actually make money doing it. Yields a distribution of winnings that does not follow a known distribution. This is not going to follow a normal distribution. We're going to say sometimes he wins $10. Sometimes they win $5 per hand. This is per hand winnings. So if I actually look at the distribution, maybe that's the distribution of winnings per hand. So every hand we say, oh, okay, well, he's got this probability of winning $5. He's got this probability of winning what looks like about $1. He's got this probability of losing $5, and this is like losing like $7 or $6 or $7. So, and there's not a lot of probability of losing this amount. Maybe it's impossible because they're playing some kind of blackjack game. Anyway, get your mind around this. This is the distribution of per hand, which is the distribution of probability. When we say distribution, we mean we're distributing the probability. Most of the probability is here around 4 or 5. 4 or 5 bucks they're going to win. And we've got the idea here. So mu x, on average, they should win about $2. Given that distribution, on average, that sounds great, right? You're actually counting cards. You should win more than you lose. So the average winning is $2, and the standard deviation, though, is $4.50. But notice this is not a normal distribution. And what we would like to do is actually answer this question. What is the probability that a randomly selected hand, one game, will result in a gain, a win, more than $0? So just a gain. So so what have we got here? Will result in a gain. And a gain, I'm defining a gain to be a win more than $0. Of course, that's gain. If I gain a penny, I'm gaining. And so this is how we write the probability sentence. The probability that X, an individual hand, what is the probability that a single, randomly selected hand, one game, will result in a gain? And there it is. But I can't solve it. I can't focus that enough. I can't underline that enough. I can't solve that probability from here because I don't have a table that tells me these probabilities. If only I could use the normal distribution, but I cannot with this distribution. So there I go. I don't have a table of probabilities for this distribution. I do for the normal. So what if I look at X bars? These are the means of size 36 because remember, under the central limit theorem, I need to pull. That's pretty non-normal. I've got to pull a large number into my sample in order to ensure that the means have a normal distribution. That is the power of the central limit theorem, is that the individuals don't have to be normally distributed, but the means will be. We can get probabilities. And not only will they, but they'll have a smaller standard deviation. Look at that. We could be more accurate. Because if I look back up there, the standard deviation of sigma x was 450. With 36 pulls, my sigma x bar is only 0.75. So that's how I'm going to find the same probability. Notice my question now is this. What is the probability that the average, notice that was not in the upper question, that the average of 36 hands, not one hand, but the average of 36 hands will result in a gain, which again is a positive win more than $0. So now look, I'm getting the probability of X bars. That's how I tell you that I'm talking about averages and not about individuals. That's all I'm saying here. I'm talking about averages. What's the probability that the average of 36 hands will be a gain? Well, it's probably pretty big. And so I would do something like this. Let's just take it line by line. There's the probability of X bar is greater than $0. That's going to be equal to, you haven't seen me write it this way. I didn't write it this way on the board, but this is just the probability of Z greater than, that piece right there is the Z-score. That's X bar minus mu divided by sigma X divided by the square root of n. N is 36. So you can put it in line right here in the equation. Instead of solving for it somewhere else and then putting it in, I'm just putting it in right here. So don't let that confuse you. This is the probability that z is greater than 0 minus 2 divided by 4.5 divided by the square root of n. I should have a closing parentheses right there. Equals, and if you do that math, that's the z-score. It's the probability that z is greater than, that number right there turns out to be negative 2.67. So I encourage you, if that's at all confusing, to go and do this problem exactly. There's nothing different here. Once I've done this part, there's nothing different. Do it exactly like we did in the last problem, and you will get negative 2.67. Then from there, it's just plug and chug. It's what we've done before. That's 1 minus the probability that z is less than negative 2.67. And we look that probability up in the table, which is why we've done all this in the first place. That probability is very small, 0.0038. So what is the probability that in 36 hands we will gain? It is very high, 99.62% chance that if we play 36 hands and count cards, we will actually come out with a gain. We'll actually come out with a gain. So fantastic, nice work. That's just another example. Remember, there's lots more examples on the PowerPoint slides. We're gonna do one more example of doing the reverse of this, finding percentiles for averages. And the only difference is gonna be instead of x bar equals mu plus z sigma, sigma is gonna turn to sigma over the square root of n. So I'll see you in video 6. Whammo! Boop.